in other places in the world, the first flux sites were being established. Also in Mexico, there are some, I'm sorry, researchers from ITSON, Jaime Garatuza with James Shuttleworth and others started to measure fluxes, water fluxes actually with eddy covariance technique. So we had that, oh, I wanted to share, okay. Yeah, the pointer. So by then, the first flux towers were set up in Mexico, and some of the longest continuous records started by then. And so this is like a decade of individual efforts. And I was saying there was a MexFlux PI meeting around 2011. There was an article by Rodrigo, and his leadership started to put us all together and to have that vision that together we can move further, right? So, but then a lot of time happened. By 2017, we got together in the Mexican Geophysical Union annual meeting to, okay, let's say we already said a few years back that we should move together as a network. So we had a sites and data diagnostic and the agreement to share the data. Whoever wanted to share it should share it through AmeriFlux repository, because we didn't want to invent the wheel, and it was agreed that whoever wanted it should do it through that repository. Okay, so after that, then a lot of PhD students and other researchers started to work with the data and with new flux sites. So we also, thank you to the leadership of Rodrigo, we were able to put up special issue. I think it's called a collection in JGR Biogeosciences. So there you can check it out. We have a few nice articles that can come out of that, of all the science that we do in Mexico with the flux towers. We also participated in a couple of Spanish publications that we thought that were important, so that we can say who we are, what we do, and to publish this daily database that was shared, and the synthesis of the annual fluxes from these sites. This was around 2018 and 19. And so then another stone that was really important was that around 2022, a lot of the sons and daughters, academic sons and daughters of the senior PIs started to get positions, but permanent positions in universities and research institutes in Mexico. And I think that we don't talk too much about it, but I think that really helped so that we said, okay, let's get together in a committee and let's do all the ideas that we've been talking, but let's do it, right? So who's going to do what? And we then we had a vision statement paper also in Spanish, because we thought it was important for us to be able to communicate within the country the importance of what we do and what can be done with the data that we produce. So we had this paper in a journal that's called Elements for Public Policies in Spanish. We didn't know if it was going to have that much impact, because it's in Spanish and it's a small journal without no impact factor or anything. But we used it in our institutions and with some government agencies so that they understood what we were doing. So we had this map showing that we cover a lot of the country. And so by then we were organizing a committee, and so we pushed for federal government recognition, which we gained in 2023 as a national lab. I'll tell you guys a little bit of what that means. And by this year, so then we finally got funds from the federal government. And so we also were successful to get a little bit of money to put together the Flux course in Spanish in Mexico. And also we were successful with a project with, like, let's say, with WWF to set up some other sites in mangroves. All right. So I wanted to highlight that, what MexFlux is a regional network of FluxNet and a proud member of AmeriFlux, but we also like to think of ourselves as a practice or community of practice. And we, the committee and a bunch of other people, we have this WhatsApp chat that it's like super active, the most active chat ever. We discuss everything from science to everything. So, so we're a community of practice of what we do, and I like to share that with you so that you could know that we are very active like that. Wait, oh God, something happened. Christine, I'm. You're right. Something happened. I changed it. Oh, I don't know either. Okay, yeah. I'm pushing everything. Okay, so yeah, so then I was telling you about the proposal that we sent to the federal government, and basically what we presented, or what the national laboratories are basically these interinstitutional networks of people and infrastructure that is distributed across the country. And the aim is to foster the development of scientific, technological, and innovation capabilities. And as a statement of public policy in Mexico now is that like science has to provide solutions to national problems and also to seek societal well-being. So it was a big effort for us to to sell ourselves to that aim, right? So we set these objectives that we have as a national laboratory. And so for the first one has to do with, we had to tell the government that we are standardized, that we do measurements that are standardized, and that the data that we provide is certified somehow. So basically this is what it means is, or for us, is that the data will be shared, with the protocols and standards that we do with AmeriFlux. So that was easy for us to, to check. Also, the most important objective, or one of the most important, is to maintain and continuous operation of the current Flux towers, tower sites, and also to design and instrument new tower sites in underrepresented ecosystems in Mexico. Another really big one, because we are convinced that education and training is very important, because we, like I was saying, we are like sons and daughters of PIs, right? And we were able to build our careers thanks to education that sometimes we got actually outside of Mexico, and we came back to develop our careers there. So we think it's very important to build and strengthen the community by different exchanges and training. And lastly, we also have this objective that we have to provide supported, to provide evidence-based decisions and solutions for whatever public policies have to do with land use change and impacts on climate and water. And that's how we presented ourselves, and we were successful to convince the government that we are worthy of being called a national lab. So then we were able to, thanks to that recognition, we were able to present a project for funds. And that's how we got a grant approved for 7.5 million pesos. Maybe it's not too much, but for us it's a lot, so that we could follow on activities that have to do with the objectives that I've told you about. So what I wanted to show you is where we are at now. All these are sites that have or currently have towers, flux towers. So the yellow dots here are where flux towers have been. I don't know if you can actually see, I'm sorry. The red line shows the sites that are currently operating, and these crosses are new sites that are being instrumented this year. And these gray crosses are the ones that are coming up, or the tower is being constructed already, or the instruments are being bought and stuff like that. Okay, so we actually have been moving a lot from 2011 to 2025, and we're really happy about it. Also, I wanted to highlight the sites that share data through AmeriFlux repository. So You can see it's not all of those sites, but we feel it's a lot of success that at least these sites have decided that it was a good idea to share the data, because we have, I don't know, we have had pushback from that for a long time. Okay, so I also wanted to show you this. Actually, I was able to put together this graph yesterday, like super fast on my phone, thanks to the chatbot, or what is it, the AmeriFlux agent that was shared yesterday. So as you can see, it's a mean average temperature and mean average precipitation, and these are all the sites of AmeriFlux repository. And in red, I'm highlighting sites in Latin America, and in yellow, the sites in Mexico. So we always say that we fill a gap, that if those sites weren't there, you can imagine we're blinded to really hot sites, and also very wet or very dry sites. So it's always important to know that our sites, even like people were saying in the session before, even if the site was only running for a year and a year and a half, if that year or year and a half wasn't there, it's a big gap for models, for our knowledge base, and whatever, and everything I'm seeing. So I just wanted to highlight two examples of what happens with MexFlux and what happens without MexFlux. So this is a work that our colleague Alejandro Cueva is leading with his student. And so this is temperature responsive soil respiration from forest sites. And the red one is without the MexFlux sites, and the green one is with MexFlux sites. And you can see here, there's a little bit of a difference. You have to go wait for the paper to know more about it, but just visually you can see that like we were talking about, some sites have a lot of value because they come from underrepresented sites. Okay, another thing that I wanted to highlight has to do with work in mangroves. It's already 10 minutes. Yeah, I'm going fast. And so the same thing, if we don't have the Mexican mangrove sites that are all over here, and we only have sites from all of the from the world that are in wetter sites, we would have different ideas on what the net ecosystem productivity is of wetlands. And this is the wetlands without all of these mangroves. And if from Flux, and the rest is the FluxNet 15 data. If we plotted wetland data from this paper, it would be around here. But if we include all the mangroves now that we have, it would be there. So really quick, we wanted to tell you guys that we have this newsletter. It's all in Spanish, but we have, here's where we highlight what we've done in the past and what we're doing now. And you can find us in Zenodo or in our webpage. And also, I was supposed to be talking more about TAFE, but you can hear the Meet the Fluxers podcast that was set up on what was the motivation of setting up this Flux course in Spanish. And I just wanted to show you that we did it, despite a lot of difficulties, but we did it. We did it. We had this exchange of educational experiences in Ecosystem Flux's workshop previous to the actual course. And here's where the curriculum or the syllabus was defined, and it was a lot of work, but we did it. This is the syllabus that we put together. It was way too much. That's the first thing we learned. It was way too much, but we thought it was a good idea to have all this, because we have people that needed to be on like a baseline of knowledge. But definitely the things that we learn are that it was just too much. But anyway, we wanted to show you that we had 120 people that wanted to go to the Flux course, and only 28 were able. But we tried to have representation from all around Latin America. And it was an incredible experience for everybody. I'm going to go further faster just to just to end up with this in a video that we have. But I wanted to say that the most important thing that we learned is that there are a lot more people than we thought in the beginning in Latin America. And this was important for not only for the students, but mostly I think for us instructors or professors, that this should foster more collaboration and a lot to advance science from underrepresented regions and ecosystems in Latin America. And another thing that we that we ended up was a consensus of how to appropriately translate eddy covariance. And I know it sounds like kind of not so important, but for us it was important. So this is how we learn, what we learn, and I'm happy to talk about everything later on. So we have time still for the video. I'm sorry, I tend to take too long. But we wanted we put together this video so that everybody could feel a little bit what it meant to be there in Veracruz during this Flux course, and with what it meant for everybody involved.
Get your tissues ready. Los flujos no conocen fronteras y la ciencia tampoco. América Latina enfrenta una paradoja monumental. Posee una riqueza natural que el mundo necesita, pero su capacidad científica para entenderla y protegerla sigue siendo limitada. Mientras tanto, nuestros ecosistemas claman por ser entendidos. América Latina y el Caribe resguardan el 60% de la biodiversidad terrestre del planeta. Pero esta abundancia se ve amenazada por la deforestación, sobreexplotación, urbanización, minería y cambio climático. En este contexto, hacer ciencia en Latinoamérica no es un lujo, es una urgencia. La solución, la educación. Por eso nació TAFE, el Taller de Aprendizaje de Flujos Ecosistémicos, una iniciativa que demuestra que la educación puede descentralizar el conocimiento y empoderar a las nuevas generaciones de científicas y científicos latinoamericanos. La respuesta fue contundente. En 2025, más de 120 personas aplicaron desde toda la región de América Latina, pero solo 28 lograron un lugar. Esta demanda abrumadora revela la necesidad de más espacios para formación es inmensa.
Construir comunidad entre distintas personas de distintas etapas de su carrera y especialmente de distintos países de Latinoamérica para formar redes más estrechas entre latinoamericanos.
Durante 2 semanas intensivas, 18 instructores e instructoras de primer nivel compartieron su experiencia en meteorología, hidrología, ecología, sensores remotos y modelación, y lo hicieron en español, la lengua de quienes vivirán y transformarán estos territorios.
Ha sido un sueño por muchos años de hacer este curso en habla española con nuestras realidades económicas y sociales.
Aquí no solo se aprenden técnicas avanzadas, se aprende a hacer ciencia con compromiso social, porque una ciencia que solo habla para sí misma se vuelve irrelevante, pero una ciencia que escucha al mundo es imprescindible.
Lo que hace a TAFE único es que es un aspecto multidisciplinario. Vemos investigadores e estudiantes de muchas disciplinas, ¿no? Muchas enfocadas a las ciencias de la tierra y otras a las ciencias biológicas, pero aquí no hay frontera para esas disciplinas.
Invertir en TAFE no es solo financiar un curso, es invertir en la única solución real, el conocimiento y la educación. Es apostar por la comunidad científica que ya está aquí, con la creatividad y la pasión para proteger ecosistemas irrepetibles de América Latina. TAFE, más que un taller,
es magia,
potencia y oportunidad.
Experiencia única
es aprendizaje,
colectividad,
reflejo de la ciencia latina,
multidisciplinaridad,
Aprendizaje para la investigación.
es en español y tenía que ser así porque es nuestro.
Es el comienzo de una red y es una declaración. Elegimos hacer ciencia desde nuestras realidades, con excelencia, con inclusión y con compromiso. Elegimos construir futuro. Con educación ganamos todos. Gana la ciencia, gana la sociedad y gana el planeta.
We have time for 1 or 2 questions.
Hi, thank you for the talk. It's obvious that the Mexican sites are very unique and kind of cover a gap in the whole global understanding of ecosystems. But with so few of the sites posting data in AmeriFlux, do you have alternative strategy for data preservation, QA, sharing, without it? And don't you feel a risk that if the data is not shared, despite being potentially important, will not be used, and then that importance will be wasted in a way?
Basically, you don't have to convince me. I remember when I registered the site for the mangrove. I remember when I registered the site for the mangrove in Puerto Morelos, and I got an email saying like, "You're the second site in Mexico," and I was like, "What?" I didn't even know that. We didn't even share. I don't know. So yeah, we have to convince our own people that sharing is beneficial, even if there are pitfalls, because there are always going to be people who take advantage or whatever. We are working on it. And for us, now that we have 8 sites sharing data, that's a success, because it's hard to convince. Maybe I'm going to say something that's not very, I don't know, but it's political, because we have a colonial legacy. We have it in our minds. It's there in how we think and how we do things, right? So we have to break that, and that maybe it's not easy for people who aren't in a colonial legacy to understand it. So we have to talk about it and to see what we should do to break that, so we can share the data, so that it can, because it is valuable, like we showed. Should I go? Sorry. It's difficult.
Thank you for sharing that. I'm wondering what are the challenges for like the instrumentations, like where you get your instrumentation, where you buy them, do you still get it from here? And for the calibration and everything, is that a challenge? And if it is, like, have you had any conversation within the community on how to address that?
This is also a bunch of other, like a big chunk of our conversations, is that everything is like 20 times more expensive to do there. Because we have to import all the instrumentation, and the government, it doesn't make it easy, because we have to pay a lot of taxes for that. And a lot of money would go to if we need to return something for like manufacturer's calibration, it's impossible. So we do calibrations ourselves, but not the factory calibrations, right? So we are trying to try to figure out how to do it, and to talk to the manufacturers to have a little bit of more, easy ways for us. But that's one of the most difficult things to do in the Global South in general. Thank you.
Thank you so much, Susanna. Oh, now we have 2 microphones. And the sharing. Okay, and then all right, our next speaker is Ankur, who will be sharing his slides.
Thank you. That's a hard act to follow. Okay, good. 10 minutes, let's do it. Gotta find my mouse. All right. So yeah, thanks for sticking around. I'm gonna give the penultimate talk, I believe. So I want to talk today, it's in this session about urban and managed lands, about an interesting landscape we're trying to understand with eddy covariance, which is agrivoltaic solar arrays. These are now, as of a couple weeks ago, registered in AmeriFlux as our Kagansa solar array pretreatment and control sites. They're kind of identified on the area. These are sites 39 through 41 of our lab that we've registered in the AmeriFlux, 90% of which are in base and 3/4 of which are FluxNet. And these are probably more interesting sites, because we spent a long time figuring out whether we could really do this. And I want to acknowledge a lot of folks at the University of Wisconsin who are involved in this project, including my PhD student, Emily Mather, who made the vast majority of the figures you're going to see, and my tower tech of 18 years, Jonathan Tom, who has maintained the vast majority of those towers that we're talking about, including our core sites. And this cool javelina mounted and on a wall agrees. So, all right. So just I'm boilerplate, I think most of you know this. We know that solar energy is one of the fastest growing and cheapest sources of electricity globally. We see this vast level of installation, particularly in China, but also even in the US. that number continues to increase despite some of the federal limitations on that. And a lot of that is occurring at what's called small scale. So not kind of the large utility grade solar, but really things that are happening kind of at the mid-scale utility. And in the Midwestern United States, as is true for a lot of the world, where those new solar installations are going are primarily on what is either working or formerly working agricultural land. So this is from the Nature Conservancy, their Site Renewables Rights site, where they try to come up with site indices for where you could potentially put solar or wind development as relative to ecosystem services that might be impacted by that. So, of course, this is a question that's been brought up in a couple different contexts of can we grow food and generate energy at the same time? And if so, what are the ecosystem service impacts? And that's been a question that a lot of colleagues, including my colleague here, Steve Lohide, who's an eco-hydrologist, has been thinking about for some time with a variety of land use conversions. And this particular idea of being able to grow food and solar energy has been around for a while. It's particularly big here in Arizona because of the work of Greg Barron-Gafford, who really kind of pioneered a lot of agrivoltaic research studies in the southwestern United States and some work in Germany and elsewhere. But there isn't as much work really in mid-latitude and temperate systems where solar energy has not been kind of viewed as a potentially big new energy source, but that's changing now. And so there's been a lot more interest in what's going on in our neck of the woods where I live. And so this is the second closest flux tower site I ever built, which is nice because I can drive to it. And so it's kind of in the urban shed of Madison, Wisconsin. This is the Kagonsa Research Campus Solar Array. It was developed by a private company, Sunvest, funded by a power utility. So they're actually, this is a commercial utility grade installation. They're producing power and selling it to the grid, 2.25 megawatts on 6.5 hectares. And we've planted, or the group has planted a mix of pollinator mix, so it's mostly rye, with some trials, as we'll see at the end, in alfalfa, grass mixes, and clover. In addition to Steve, Chris Kasharik, who is an agronomist and runs a bunch of ag ecosystem models. So this red circle, that's where my office is. That's where Paul Stoy's office is. And somewhere in that circle, also both of our houses are in that circle. And then 17 kilometers away is where the University of Wisconsin Physical Sciences Lab is based, and the land next door is where they've developed the array. It is a 2.25 megawatts, and I just want to keep this little, this was a question that Andrew actually asked me about, what is the actual energy balance if we also consider energy production? And the peak power production here is 2.25 megawatts, so not accounting for capacity factors, the maximum energy usage for this particular site would be roughly 35 watts per square meter in terms of going into electricity. So keep that in mind because it'll show up again in a sec. All right, so here's what the towers look like. We have our tower on wheel that used to be USCS1. It's now USKSP because we've moved it. That's our pretreatment site that we did the prior year. I won't talk too much about that because I'm still working through that data. The control site is we moved those instruments onto a tower in a nearby farm field. So it's really not exactly the same, but it's close enough to say, what would this land be if it was not in a solar field? And then the actual tower we have here, currently at 9 meters, we could raise it to 32. I'm still trying to figure out how to actually get a footprint of this site because of its very complex heterogeneity. This is the kind of site that most people tell you is it violates every assumption of eddy covariance out there. That seems to be my specialty. And so this is where we put it based on some work that we had an undergraduate work on some footprint models, and we kind of said 9 meters seems like the sweet spot to get us out of the roughness sublayer, but still be mostly sampling the array. And here's a field trip. We get to wear hard hats and yellow things in this site because it's a commercial installation. And Jonathan's pictured here. Emily's in the middle. Jen Kell is the undergraduate I mentioned, who's now a grad student who did all the footprint modeling for the site to tell us how high to make the tower. We have a PhenoCam that just went online a week ago as well. Thanks, Andrew. It doesn't really look all that interesting. We're going to reposition this because I want to capture more of the actual rows, but this is what it looks like right now. One of the real questions we can ask here is, can we actually kind of use the greenness and the difference between, and especially if we can get thermal imaging going here, we can start to look more at what's happening in the panels itself in terms of the energy balance. So, the very first thing I like to do is is this a really dumb idea to put a flux tower in a solar array? Because apparently we are the first people who have ever done it in FluxNet. There's maybe one other site in France, but they've never published their data. according to George Burba. And so this array has so this is comparisons between the control site and our array site. They are different heights, so you do have to take that into account. The main things we see is, I was trying to see is like, are there weird anomalies? And for the most part, not really. TKE, which is a good estimate of turbulence, kinetic energy measured by the sonic, doesn't really show. It's higher in the array, no surprise. There's a little bit of recirculation. You can feel it when you walk into site. We looked at wind directional impacts. So this is just NEE as a function of wind direction for all times. And nothing really sticks out, right? Like, we need to do a lot more. This is first light data. This is data from June to October 10th, 2025. It is now October 24th. So some of these are slots I've only seen in the last week. U-star with wind direction, another good way to understand. There is a little bit of a slope on the site as well, but nothing really sticks out in comparison of the array and the control site. This was one that Emily sent me last night at midnight, so I added it at 1:30 in the morning. Don't ask why I was awake then. And one of the things that you can see is that this is a cumulative energy imbalance between the array and the control. And since Andrew asked me, could you potentially detect the difference, is that related at all to the power production? I don't know yet, because I'm still trying to get to power production data from the company. But that difference is roughly 300 megajoules, which if you average that out is around 30 watts per square meter, which is not that far off from what I said was the maximum capacity energy difference that is being used. So this can't be all of it, because of course capacity would suggest most solar arrays produce about a quarter of what their max capacity is over the year. So that seems like maybe also some other energy imbalance issues potentially related to large eddies or things happening with the panels themselves. I don't know. But here's first light data on cumulative NEE and cumulative ET over summer 2025 in the array in blue and the control in green. You can definitely see that it's a weaker CO2 sink and is a slower ET by about 50% in most. But I want to point out a couple management intersections. So we had some mowing in the array. And the first one, you can kind of see that on impact on the top, on the cumulative CO2. Not so much, but certainly in the ET, in the cumulative CO2, you see a little bit of a slowdown, but not so much in the ET. When they added a bunch of herbicide, glyphosate, then you definitely see a big difference, right? That really killed out a lot of the plants in the array, and that really shut down the CO2 uptake. It didn't really change the ET. It's a pretty energy limited region, so you're just going to have water's going to continue to stick around. What I'm more interested, though, is this really interesting period in late July and August. And you'll notice that during that period, both the array and the control and the CO2 are kind of like not doing too much. And we started thinking a little bit about what's going on. And this was a really interesting summer. The last few summers in the upper Midwest, we've had quite a bit of Canadian wildfire smoke. And the amount of just smoke-related radiation changes were particularly large, especially that period in time. So this is just a loop around late July, early August, where we had a particularly large smoke event that came from Canadians. And we did put a shadow band radiometer on the site so we could look at diffuse radiation fraction. Here's that same time period. It doesn't really stick out because we have quite a few of these events through the summer in addition to the usual cloudiness type things that happen in the Midwest. And so what we did here was just a really simple thing of, if you looked at the relative, so on the x-axis is total incoming radiation, and the y-axis is fraction of diffuse radiation, and the color here is the flux, water on top, CO2 on the bottom. And the main thing I'm seeing so far, and this is again a very cursory analysis, is at highlight, you do see that large difference in CO2 and ET flux differences in the control and the array. But as you get to more and more diffuse light, the differences between the two sites kind of start to disappear in terms of a relative difference of the amount of CO2 uptake in ET under diffuse light. And that really points out to the other half of the study, which is what do we do with partially shaded ecosystems, right? And so this is where we're studying. My timer's not moving, so I was done. It's been like 8 minutes. All right. You just are very, very polite then. So I will just sit. What's that? But I'm going to get to the last slide then. But basically, a lot of the work we're doing now is on the ground, which is really looking at what is the role of shading on kind of partial growth, leaf area index? What is the role of water distribution? So you see a lot of growth happening in the drip line. So a lot of the water gets redistributed. We tend to see increasing water tables. We had an undergraduate and a high school student this summer. Liz and Mary here on the bottom work with faculty in geography and fly some drones and look at some temperature gradients. We did some fun thermal imaging where you can really see the solar panels sticking out. So I think this would be a fun study to stick in a large eddy simulation. Under the panels is a really different story where you see a diurnal cycle and whether it's cooler or warmer or wetter or less humid. And we've done a bunch of chamber measurements. Basically, the main thing we're seeing is the partially shaded plots have the highest CO2 uptake. And then the last thing I'll just say is the thing we also just did toward the end of the summer is get some hyperspectral imaging going on a drone with Phil Townsend in Wisconsin, along with his technician, Elliot Marsh. And on the right is just an NDVI, a really rough NDVI plot I made. And so it's about as good as my coding skills. But the thing is, you can definitely see the trial plots on some of the rows here. And in some of these are fixed arrays over here, and these ones are solar tracking, and so we're kind of comparing the two here. And you can see the row with the flux tower is a little bit wider. That was done intentionally during construction to allow the flux tower to exist. So a lot of cool questions here. We have 400 bands of data I don't know what to do with at 0.6 centimeter spatial resolution, but hopefully we'll get some repeat visits and start to understand what's going on at this site. And thanks for letting me go a few minutes over.
We can take one question.
Scott.
You hinted intriguingly that the energy difference between the two sites might be at least partially accounted for by the actual energy production of the site, but I didn't quite get, maybe you didn't have an answer yet, but what is your thinking about that?
Yeah, what I really would love to get is either a model of the total electricity production or actual raw data. And we're just in conversation. One of the challenges of working in managed lands is that managed land partners need to understand what the heck you're doing and why they should share data with you. But basically my back of the envelope calculation suggests that at least there is a chunk of that could be explained by energy going into electricity production. Of course, the sensible heat flux, which I didn't show, is quite a bit higher over the site as well. So the other big energy term here is the panels that are particularly hot, and that's going to create some sort of larger eddy circulation. That's been a major source of energy imbalance in a lot of sites, I will argue, based on the Chapman Conference on Energy Imbalance that we had a few weeks ago. And I think that's something that I'd love to dive a little bit more into at the site to see how much is that large eddy contribution occurring because of this very nice regular pattern that looks almost exactly like all the LES studies where we generate large eddies and see that impact on fluxes. So this will be a fun test case for that as well.
Awesome. Thank you.
Yeah,
Thank you so much.
And I do have to run to the airport, so I wanted to say goodbye. It's so great to see you. I miss you all. See you soon.
All right. Our next speaker is Kyle, who will be talking to us about scalable carbon flux estimates in restored wetlands. And then I'll put it on. And it won't make a noise. It'll just slowly disappear.
All right, last talk. I'm Kyle Delwich. I'm a research scientist at UC Berkeley. Today I'm going to be sharing some of the work I've been doing lately to come up with scalable carbon emissions estimates in restored wetlands in the California Delta using data model fusion. And before I start, I want to acknowledge this work is built on really decades of work done by a tremendous number of people in the Berkeley Biomet Lab led by Dennis Baldacci. All right, so I want to take you to where I work. So I'm from California. I work in the red outline there is the Delta region of California. The green outline is the watershed for the Delta. This is a tremendously important area for the state of California. 40% of our runoff flows through the Delta. It supplies 2/3 of the drinking water for the state of California. All the water for Southern California gets pumped down from the Delta. And it funds billions and billions of dollars worth of agricultural projects. So it's a critical area in the state, critical ecosystems, and highly vulnerable to change. Historically, this was all a wetland. And then in the 1800s, the Europeans came and they drained it primarily for agriculture. And this is what it looks like now, by and large. It's a patchwork of farmlands, levees, and rivers. So there's been a movement, especially with some state agencies, to start restoring some of these patches of lands to wetlands, and that's for many different reasons I can talk about later. Subsidence reversal is a big issue in California. These areas are subsided, sometimes 5 meters below sea level, so reversing that subsidence is critical. You also have some really great carbon sequestration. So some of these ecosystems are the most productive ecosystems recorded on Earth through the data that's submitted to FluxNet. So that's exciting for us as scientists, so we can measure CO2 uptake. There's also, my methane emission. There's also methane emissions. I guess that arrow disappeared. So we study all these different things, but a very practical problem we're dealing with is how do we fund the long-term maintenance of these sites, and how do we promote more restoration? So there's often, or there can be capital funding to create these restored wetlands, but then how do you keep them healthy in the long term, because a lot of them are still artificial anthropogenic systems. And so one thing, oh, there it is, methane emissions, yay. So one avenue that we're exploring is whether or not we can use the carbon market and carbon credits to fund the maintenance of these systems. And so the state of California, the Department of Water Resources, is particularly interested in this because they have numerous wetlands. There is a voluntary carbon market protocol through the American Carbon Registry for the delta and coastal wetlands of California that lays out how you would quantify your carbon sink for your delta wetlands. This is the list of procedures they allow for quantifying them. Not surprisingly, ecovariance is on the top, the gold standard. Biogeochemical models are promoted and allowed, and then there's a few others there. But I will point out that so far of the credits that have been generated have used those top 2. So that's great, but one of the practical problems, as we all know, ecovariance can be very expensive, and for a state agency without a lot of money that wants to build a lot of these wetlands, that's a hurdle. So biogeochemical models are nice, but then there's an accuracy question. And so the goal of this work is how do we blend the two of these to create what is still an accurate annual estimate of carbon emissions, but it is hopefully a bit cheaper than a tower at every single site. And so we do this using data model fusion. The model that I'm using here is Peppermint. This is Patty Oikawa's model, and I'm using this because it is specifically called out in the protocol as a model that can be used, and it's the only one that we've used thus far, so the carbon creditors are familiar with this. So we use this Peppermint model that models carbon in the delta, and we combine it with short lengths of ecovariance data, where the idea is that if we had a mobile tower that could travel around to many different wetlands in a year and get data from those sites, could you then compare the short duration data, put it into the model, and come up with an accurate annual estimate? So that's the goal. And this would lead to, in theory, better and cheaper annual carbon flux estimates for this carbon crediting purpose. I won't get into too much of the details of how we do this. There are biogeochemical equations in the Peppermint model that look at things like substrate affinity, enzyme activity. Some of these parameters are optimized in the model within an appropriate range. And so I've gone through, taken this approach using data modeling fusion and optimize these parameters for small subsets of the year, and then applied the model to the whole year to see what the results are. And if you need convincing that this is necessary, this is the Peppermint results in gray, and then the actual field data in purple. When the model was built 10 years ago, before 2015, the agreement was great. Since then, it's not so great. So clearly, we need to do something to be using this model. So these are the main questions that I need to answer, that the Department of Water Resources wants to know is, when in the season would you be deploying these mobile towers? How long would they need to be out there? And then how frequently would you need to go back and redo this? So this is one of the first plots I'll show you, and I'm going to walk you through it. This is for methane, and for the sake of time, I'll just show you methane. What this is showing on the x-axis is the starting day of that training data. So for 100 there, that means I started the training data on day 100, and this is 2 months of data. So I used 100 through 160, optimized the model parameters, and then applied the model to the entire year. Y-axis is the modeled minus measured, so just the difference in what we measured versus what we modeled. Ideally, we want to be on that 0 line, perfect agreement. The plot in the purple line, solid line, is the average result over, in this case, 10 years of data, and then the dashed line is the standard deviation. And so you see for methane, for this is just 2 months of data, on average, it does a great job if you're between, day 100 to day 250 or so. And this is not terribly surprising. The growing season has more information. But on average, it does a very good job of estimating these annual carbon emissions. But that's average. There's a lot of uncertainty. So then you can increase the amount of data. And so this is the same result for 4 months of training data. And you see you do cut that uncertainty down quite a bit, perhaps in half, but there is still a fair amount of uncertainty in there. And so the question of how much uncertainty is tolerable is perhaps slightly subjective, but I think there's a lot more work we can do to improve this. The uncertainty, that is. Okay, so that's exciting. It shows us that we can do this if we put these towers out in that growing season area sometime between April and mid-September. How long do they need to deploy? This is sort of the sticky question. It depends on your uncertainty tolerance, and this is something we'd need to work with the carbon crediting verifiers to figure out what is, what they're going to tolerate. Oh, yeah. Okay, next question is how often would you need to do this? Okay, so this is 3 different sites that I ran this process for, and I looked at if you optimize the model with data from 1 year, and then you ran the model for say 2 years ahead or 5 years ahead, how different would your results be? And so the x-axis, and now this is a ratio, sorry, on the y-axis, a ratio between measured and model, so you want to be at 1, and then the x-axis is the years of data, the difference in the number of years. So at 10 years, you're running your model on parameters from 10 years ago. And the answer varies based on site, perhaps not too surprisingly. East End Wetland, doesn't really matter. You could use data from 10 years ago. The model would still be quite accurate. Mayberry, that one with that really long-term trend, there's problems there. But I think, we can improve the model, I think, somewhat to accommodate that trend. But, on average, I think a few years. You could re-optimize this every few years. So if you had 1 mobile tower, maybe you can cover, say, 8 different wetlands in a few years. And so for the Department of Water Resources, that's valuable because they can't put up 8 more towers, and frankly, we can't service 8 more towers. So every few years. All right, I have 1 minute. Next steps. So there's work to be done on improving the model to reduce some of the uncertainty. I didn't show you CO2, but there's ironically more work to be done on CO2 than methane, which is not usually the case. But we're also working with the California Department of Water Resources, like I mentioned, is quite interested in this idea. We do have contracts in process with them to actually start deploying one of these systems. And then, so I presented this for this practical application of the delta wetlands and this particular model that we're constrained to use because that's what's in the protocol. But we could do this for any model, right? Data-driven models or other biogeochemical models and look at, what is that trade-off and how much data you need versus your uncertainty tolerance. And, I think there's a lot of exciting work that could be done there. All right, thank you.
Hey, oh, we already have questions.
This is really great, Kyle. Thank you. It's cool to see such a practical application. So it seems like the timing is great analysis and really informative. Have you thought about how you go about deciding where to put it in the wetland based on spatial variability, remote sensing? Any thoughts there?
That's a good question. I haven't thought about it overly because I think the question of where to put in the wetland is sort of a practical consideration if you're talking about a mobile tower we may get a trailer, so it would have to be on a levee road or somewhere practically. I mean, in the future as we do this, I would look at the spatial distribution of, in our case, open water versus vegetated areas and try to make sure the footprint is representative. But so marry that with the constraints of the practical, where can you drive this trailer with this tower on it?
Yeah, that's so cool. To my knowledge, that is the only protocol in any major registry that has eddy covariance written in. And you all are obviously specialists in wetlands and methane, but have you thought about extending to other ecosystems, croplands or grasslands, the notion of short-term tower collection, or any thoughts on how we could advance this sort of protocol approach in other land uses?
Yeah, I mean, I mean, frankly, I haven't thought about it too much beyond wetlands, but I think that the framework and the idea is simple enough that, we have all these data, we can do this, right? I mean, if you have people have asked me about, oh, well, I want to do this in such and such ecosystem. I'm like, well, to do it this way, you need a biogeochemical model, you need some parameters, but there are also data-driven models. So, I think that recognizing that there's a barrier to putting out permanent towers, and this could be a tool to try to expand the benefits of eddy covariance in a slightly less expensive way. I think is worth doing and valuable.
Any more questions? Maybe one more, if there is a lingering one.
Thanks, Kyle. This is sort of off the main topic of methane, but I was wondering, you talked a little bit about how restoring wetlands can reverse the impacts of subsidence. And from an engineering background, I was always sort of under the impression that it was mainly irreversible. And I was curious, because it looks like the Department of Water Resources is interested, so maybe that's related. I was wondering sort of how restoring wetlands does reverse that, and how you could maybe monitor that with towers, if that's something you're looking at.
So I could talk a lot about the delta. But so when these ecosystems were drained, it's peat, carbon-rich peat, exposed to oxygen, it starts to oxidize, right? And so we're losing tremendous amounts of CO2. And so every year, the land surface goes down a few centimeters per year, and it's still dropping. And that's why in places, you're 5 meters below sea level, right? And the ships are going by above your head. But as soon as you flood it, you stop that oxidation process. So you halt the subsidence, and then you're building the peat back up. It's very slow, like maybe a centimeter a year, less than a centimeter per year. So, it's a very long-term process, but it took, I don't know how long for these things to develop. So, yeah, you're reversing subsidence on a very slow timescale, but you're also stopping that loss. So, it's becoming increasingly expensive to keep these systems dry for farming because they have to pump the water out. So it gets harder and harder to do that. And so and the levees get more and more unstable, which is a huge cost burden for the state of California. So there's a lot, depending on what pool of money you pull from, the state of California either can or can't care about carbon, but there's a ton of money in just levee stability. And so in that sense, like even if you don't care about carbon, just flooding the land and stopping the subsidence is beneficial.
Well, thank you, Kyle. And thank you to all. Thank you to all our speakers in that session.